All right. Still won't do that. All right. All right. I wanted to get, here we are, circulation. Is that one visible?
Yes, we can see it. Looks good.
Good. All right. Okay. Are there any questions? How many people do we have right now?
Well, we only got 31 so far.
Well, they get a little more time. They're getting bored.
They are. Better throw in a quiz during lecture or something.
Well, where are we now?
34.
Oh, okay. Well, we'll go ahead and start regardless. Just at this point, it's a surface, an arbitrary surface within the flow field, and with velocity and all the other stuff going on. And the boundary of this surface S is closed, but it's an arbitrary surface, and the boundary is C right here. We define circulation, and this will picks up on vorticity at the same time soon. And this is the definition. We use a capital gamma, and it's the line integral of v dot ds around the closed curve, any closed curve. As I say here, the minus sign is due to, we call clockwise gamma positive, whereas normally the positive direction for ds is counterclockwise. And right away from Stokes' theorem, we can convert from a line integral v dot ds to a surface integral of del cross v, which is a vector, dot ds, which is a vector. Why do we want to do that? Again, it's an arbitrary surface with an arbitrary perimeter C, and now we shrink it. And we go from this equation, we just basically yank the integral sign off it, and then we say that d gamma is the integrand. Okay, and then we clean it up a little more. Instead of using ds, the little vector, we replace it with the unit vector n ds, and the dot product is then just the del cross v is one vector and n is the other. And n is coming out of S, the normal to ds. Well, then we can flip it around, and then we can say d gamma ds is just del cross v, minus again, of course, dot n. So this is the differential, well, just normalized with ds, just pulling this out and bring it over here. Now, earlier, I warned you that gamma circulation is a good friend of vorticity, and we had defined del cross v as C, the Greek letter C, lowercase, as vorticity. So we can then we can replace d gamma ds with vorticity dot n. And then we shrink ds to a point, and then we just say the vorticity normal to ds is equivalent to the circulation per unit area, back up here. Why did we do that? This is a lot of elegance, but again, I like to remind people that all this foundation work was done before computers, and even before pocket calculators. Everything was, there were adding machines, of course, and so you could use those. And then for multiplication, division, square root, and all that stuff, you had a slide rule. And so you just didn't just say, hey, sum all these things up and push enter, and you got the answer. They were going down to first principles. And I worry that if we had started looking at aerodynamics with computers available, we might be further behind now than we are. All right, so let's move ahead a little bit here. And I jump all of a sudden, okay, we got circulation defined and vorticity defined. Stream function, this is something quite physical. And now let's jump, and we have to jump exclusively to 2 dimensions right now. The stream function has no meaning in 3 dimensions. So consider a steady 2-dimensional flow. And we already developed this equation that the slope of a streamline is just the vertical velocity divided by the horizontal velocity. So we know what the streamline is, or we know what a streamline is. And then if we know u as a function of x and y and v as a function of x and y, we can integrate them to get an equation of the streamline. As I say, an algebraic equation. And this is, you always like to use f of x, y, or whatever equals a constant. That's kind of a generic way of representing it. But we're going to get specific. We're going to have a psi bar, capital psi bar of x and y equals c. Same, I mean, this is just changing notation from here to here. But we're calling this the stream function. Now think about having an arbitrary flow. In the wake at infinity, you know what it is, just a bunch of parallel lines. But as you get closer to a body, they're kind of form a family of shapes. And we say, hey, if we change this number, c, we'll get a different streamline. And for instance, you get something like this. Here's with one value of c, number one value of c. Here's with number two, and we're saying for this flow and the way we define the streamlines, C2 streamline is above C1, two-dimensional. And this is for an arbitrary flow where we know now the geometry of these streamlines. Once we know little u and little v. And all you have to do is pick one point on the streamline and you get its whole shape of the streamline when you integrate. Now we say, we've defined a function and just renamed it. But we say that this psi bar represents the difference, delta psi bar, between streamlines AB and CD, and that difference is equal to the mass flow through here. Here's velocity, and it's the mass flow. Well, that's got a physical meaning right away. And hey, what comes in this side has to go out this side. So the continuity equation is starting to show up here, conservation of mass. And if we're talking conservation of mass, that says that this has to apply everywhere along here. Between these two streamlines, the mass flow is constant. I had a student that should have known better say years ago, I think I was teaching at the University of Illinois, Professor Liebeck, what about the flow across the streamlines? And his name was Ralph. And I said, Ralph, listen to what you just said. Well, can't there be flow across a streamline? And it isn't a streamline. Okay. None of you would think of that. So we've crudely defined this, and so we have a delta psi bar is equal to rho v, that's the mass flow, delta n, which delta n is the space between, physical space between the two streamlines. So we can write it this way. Well, you know what's going to happen. You just say rho v is equal to, the limit is delta n goes to 0 of delta psi over delta n, or partial of psi with respect to n. And this is a big deal in that if you know psi of xy, taking its derivative with respect to n gives you the velocity. If you know the stream function. Well, wait a minute, let's see. And here are two different streamlines. Here is psi bar, and here's psi bar plus delta psi bar. And I'm in Cartesian coordinates here. And we can say, looking at this, okay, this is delta n, this little vector here across. That's the distance between the two streamlines. And here is v showing up here, and v and little u. And we said this is supposed to be the mass flow. Well, taking, okay, little u, it's carrying of mass across this delta y. And little v is carrying this flow across minus delta x. So seems a crude way, a cumbersome way to write this, but hang on. We get rho u delta y plus rho v times minus delta x represents delta psi, the mass flow. And okay, taking the limit, we just get d psi is equal to rho u dy minus rho v dx, psi bar, I'm sorry. But in general, just ordinary math, the differential of psi bar is just partial of psi with respect to x dx plus partial psi with respect to y dy. This is just a math expression. Well, hey, let's compare this expression for d psi with this. Bingo. Rho u is partial psi bar with respect to y. Rho v is partial psi bar. There should be a bar up here with respect to x. And if we go to incompressible flow, we can throw away rho. In other words, rho equals a constant, so we don't need it there. And redefine psi without a bar on it as just psi bar over rho. So again, given this function psi of xy, we can get u and v anywhere in the flow field. Just take its derivative. Now we don't quite have psi of xy yet, but we're talking about it right now. And the other thing, do this yourself. We will find that very often it's better to work in polar coordinates rather than in Cartesian coordinates. And here's that same development, but in polar coordinates, left to the student. But here's the answer. Again, this is the radial velocity in the polar coordinates, and this is the tangent or the circular velocity, v theta. Works. And we'll find we'll use this representation at least as often as the x and y. Okay, we've defined the fundamentals of what a stream function is at this point in both Cartesian and polar coordinates. There is an associated function that's every bit as important. We call it the velocity potential. And what we're talking about here right now are the fundamentals of everything we're going to do down the road. And remember, we said if a flow is irrotational, del cross v is equal to 0 everywhere. That doesn't restrict us much because, as I said before, absent viscosity, you can't have rotational flow because you can't apply a couple to create rotation. So if we have an onset flow coming up to an airfoil, it's all parallel flow upstream, and as it comes to the airfoil, the flow goes around the airfoil. But if it's in viscid flow, you won't get there's no boundary layer, and you get the solution for an incompressible irrotational flow about a body. Gee, is that all we need? Well, we've got to qualify. We're going to qualify that some, because we will find then that any body we represent in pure potential flow, as we'll call it, can't have a force on it, drag or lift, but we'll be able to make a force on it. Okay, there's going back to a math book, you can go hunt this up. The vector identity for a scalar function, phi of xy. This hasn't been mentioned, but if an arbitrary scalar function, there are all sorts of rules about it if you're a mathematician. But for flow, just saying, hey, I've got some scalar function. There's something that's varying in a flow field. It could be velocity, it could be density, whatever. Del cross del phi is equal to 0. For us, this is just math. But we are saying here is del cross v here. Well, now this is equal to 0. This means there is this function phi of xy exists, and we call it the velocity potential, just out of this vector identity. And that velocity potential, then, we can say it's v, is del phi, like this. Now, to get a little elegant, this is what we call a reducto ad absurdum development. We didn't start out with phi. We said, hey, this implies there's such a function, and we'll call it this. This is all legitimate mathematically. Well, what do we know about this? We define it this way from this, del cross v. V has 3 components. Notice we're 3D all of a sudden right now. We said for an irrotational flow, this exists. And then the vector identity says, hey, we can represent v as the del phi. We can represent v by del phi like this. As I say, it's a reducto ad absurdum proof. So it says, if then a flow is irrotational, there exists a scalar function phi such that the velocity field is given by the gradient of phi. This is very powerful. So we've defined these 2 functions, stream function and the velocity potential. Stream function maybe has, it was derived has a little more physical meaning, but what do we know about them? We've already talked back when we defined gradient of a field. So looking at that, we could say phi equal constant is an equipotential line in the flow. And a line everywhere in flow, everywhere tangent to del phi, tangent is a gradient line. And since del phi is equal to v, as we defined it up here, this is also, del phi is also a streamline. The gradient line is a streamline. Okay. Gradient lines and equipotential lines have to be orthogonal. So psi and phi are perpendicular to one another. Okay. What does that allow? Going back to, for 2D incompressible irrotational flow, psi, if we have a psi equal constant, hence along a streamline, we get this. And we also get d psi is equal to this. But along a streamline, they're both equal to 0. Or we already showed this, just that in a 2D flow, two-dimensional flow only, we can say that the slope of the streamline is just v over u. With the caveat, of course, that psi equals constant. Slope is v over u. Similar, and then we say, well, okay, here we're psi of xy equal constant. Here we are, let's look at phi of xy equals constant along an equipotential line. And we have this definition of d phi looks like this. Notice the psi looks like this up here. And we can also write d phi as u dx plus v dy. So then taking this equation, dy dx along for a constant phi gives us minus u over v. Up here, dy dx along a streamline is v over u. What do we know about negative reciprocals of a slope? Right here. That just shows that the streamlines and the equipotential lines are orthogonal. And to kind of help ingrain this, this is kind of a summary. Note, u and v, this should be r, not or, are obtained by differentiating phi in the same direction as v. Psi is obtained, u and v are obtained in a direction normal to v. Again, phi is defined for irrotational flow only. Otherwise we don't get the, this requirement doesn't meet this. You've got to have irrotational flow to have a velocity potential. Same time, phi applies, the velocity potential applies to 3D flow also. Psi only two-dimensional flow. So at this point, for a two-dimensional, irrotational, incompressible flow, we've got this pair, psi and phi. And here's the other, do it for yourself. You're going to want to have the polar coordinate versions of for velocity potential. And well, okay, I want to back up here for those that are mathematical. In 2 dimensions, how far back do I have to go? A little bit further. Yes. 2 dimensions, this is for an irrotational flow, ds cross v equals 0. In the xy plane, you have this equation, u dx minus, v dx minus u dy equals 0. These two equations don't apply in 2 dimensions, in 2-dimensional flow. This one does. So you got v dx minus u dy equals 0. And then if you go to 2 dimensions and take the divergence of v, I'll stay with it. You get u dx plus or minus v dy equals 0. Let me get the right word. I want to get it more consistent to math. Let me bail on that right now. But it turns out they are the Cauchy-Riemann equations for analytic function theory. And when you do this in complex variables, which is a nicer way of doing it, but Anderson doesn't do that. Okay, now we'll apply this stuff a little bit. You probably ran across Bernoulli's equation in high school physics, maybe, or certainly by now in your undergraduate education. But we're going to derive it using a machine gun instead of just some simple math. Let's look at, and this is useful though. Consider the case of a steady, incompressible, inviscid flow. I haven't said any, what have I left out? I haven't said it's irrotational. Incompressible, inviscid though, and steady, of course. And so if we take the x component of the momentum equation we defined a couple of days ago, and here I show the substantial derivative, but I add on that the partial u respect to u is steady flow, so we get rid of this. And so this becomes just, well, I've multiplied it by dx already to ruin it. But the equation would be, this equation here would be u du dx plus v du dy plus w du dz is equal to 0 equals minus 1 over rho partial p with respect to x. Moved rho over this side. But I multiplied it now by dx, each term by dx, all the way across. And that should apply anywhere in the flow. We haven't broken any rules. But now we're going to jump to 3D, so we won't be playing with a stream function right now. But consider the 3D flow. Now we're going to restrict it along a streamline in a three-dimensional flow, but it's irrotational. So a couple of the other two things back from, remember, the different, the thing about a irrotational flow, these are two of the components of del cross B. And why do I want these? Because I can substitute these into some of the terms here. And I didn't change the first term at all. But the second term, I changed stuff. And the third term for per irrotationality. You can check the algebra on doing this. I didn't mess with this term. But what I have now is u partial u with respect to x plus u partial u with respect to y. You can see what I did. Plus u partial u with respect to y. And here's u partial u with respect to z, just replacing via these terms. Here's how I got rid of the w, and here's how I got rid of the v. So now everything is in u. Now, again, just a regular differential. The du is partial u with respect to x, dx plus partial u with respect to y, plus partial u with respect to z. And the Euler equation in the x direction can be written like this. But really, if we look at this, we can just say u du. Oh, wow. We've got this done, and if I can factor out du out of here, and it just reduces to u du equals minus 1 over rho partial p with respect to x dx. This is just mostly algebraic manipulation. Or I can write this as 1/2 du squared is equal to this. I can do the same thing in y and z. So now I've written these three down. And then, again, just the differential of dp is partial p with respect to x dx. And I don't want to read the whole equation. We can add these three up, and we can say 1/2 d of v squared is equal to minus 1 over rho dp. Or dp is minus rho v dv. Now, if we have, we can say, hey, this is valid in this steady, incompressible, inviscid flow. And now, again, incompressible. We can integrate this equation from a point 1 to 2 along a streamline. We can do that. So it looks like this, and integrating it, this is just P from 1 to 2 is P2 minus P1. And over here, integrating V, oh, damn it. Integrating v, we get a v squared and a half out in front. You ever seen that before? P plus 1/2 rho v squared is equal to a constant, namely called the stagnation pressure, total pressure, along a streamline. So there's a machine gun version of Bernoulli's equation. All right, at this point, it's only applicable along a streamline. But if we allow rotation, that this constant, this one, if we allow rotation, the constant will change. But if we restrict it to irrotational flow, the constant's the same for all. It looks like this. Now, to get some insight on that, now you've got a flow field. And we get this boundary layer, but a boundary layer has viscosity, and the flow is zero at the wall, and a short distance out from the wall, you've got the potential flow velocity. But within the boundary layer, you have viscosity effect. Well, within the boundary layer, the flow is rotational. And within the boundary layer, the static pressure is constant. Go back up to this. Static pressure is constant. Otherwise, there'd be flow across the boundary layer, which there isn't. The static pressure is constant. The velocity at the wall is zero, and the velocity up at the edge of the boundary layer is v. So the total pressure varies within the boundary layer. But Prandtl showed that this boundary layer is confined to a thin thing for its depth is not very deep, and so at the edge of the boundary layer, the velocity is, you can assume, is the potential flow velocity. And if we ignore and if we have a streamlined body, you can't believe me, we can't ignore the boundary layer. But for a streamlined body, we can, in essence. And now we've got, hey, upstream, the flow is parallel and uniform, and so it will be on all the flow outside of the boundary layer for the flow over the body. And so that flow out there we call potential flow. And boy, are we going to be able to solve problems with this. Because as I said, to get elegant about it, we can go to analytic function theory using complex variables, and all the math works faster than the way we're going to do it. All right. Well, what can we do with this incompressible flow in a duct? And here we assume that the duct, there's no cross flow, and it's uniform flow, and we can say it's actually one-dimensional flow. And analyzing this flow in a duct, arbitrary duct, one-dimensional flow, and for steady flow continuity, just BDS. You can see we got to go yank the elegant equations out. And here's the continuity equation. But we don't have flow through the wall, so that goes to zero. And we get the integral, I don't want to get to that yet. We get the integral, this is the flow in and this is the flow out, and we can integrate it, and we say minus rho AV1, because we need to remember the DS is pointing out, plus rho 2, A2, V2, or we get rho 1, A1, V1 equals 2. That at 2, or if it's incompressible, we get this simple relation. Again, what is important is now we've got a very simple version of continuity, and we have a very simple version of Bernoulli equation, or momentum, and continuity and momentum, trying to analyze something that we can't see, air. And look at this in a wind tunnel. In a wind tunnel, there's something that we like to know, and that's the velocity in the wind tunnel. So we put we take pressures at the entrance area. Here's the test section. We take the pressure in the test section. Well, this says the flow in the test section, V is going to be higher than V1, and hence the pressure via Bernoulli's equation will be less. And again, now you could measure P1 and P2 separately, but there's some error. Instead, you just put a U2 around here, and you get a change in height of the working fluid in here, oil, or if it's a high-speed tunnel, mercury. And here I use W as weight per unit volume for this fluid in here. Okay, I can solve this Bernoulli equation for V2, and it looks like this. And then I can replace V1 with the area ratio times V2, and then we get V2 squared, just using Bernoulli's equation, is 2 over rho times the static pressure difference, which we're measuring here, plus, oh, damn it, V2 squared. We can solve this for V2. And to make it easier, incidentally, you know this geometry, you know A2 over A1, and you can leave P1 minus P2 in here, or it's 2W, the weight per unit volume, times this height difference that you measure. And that is the way we measure wind tunnel velocity, especially low speed. And usually there's a ring of static pressure taps around here and here, and it's very accurate. Now, the other thing you can, so there's a velocity in the wind tunnel, but you'd like to know, hey, if you're flying an airplane, one of the most important things is your airspeed. Because if it drops too low, you're not flying anymore. So how do you measure airspeed? Well, you measure total pressure just by sticking a port facing straight into pressure gauge. So that'll give you stagnation pressure. But we can solve this equation for V. So, okay, I've got the stagnation pressure. All I need to do is measure the static pressure. But this simple thing is called a pitot probe. And in order to get airspeed, we need a good measurement of the static pressure. And where do we get the static pressure? Well, here's P0. This is a sketch of a pitot static probe. And here on the side of this probe is a static port. And usually there's a ring of static ports. The harder pressure to measure is the static pressure. And I'll talk in a second a little more about that. But just saying we can measure that. Now, all we have to do is hook these two pressures up to a gauge, and we will know the speed of the airplane. And if that gauge is calibrated for a row, but we don't know density, do we? Well, a pitot-static probe that goes to a gauge, in the gearing of the gauge to measure, to indicate the velocity that what you want to know, it's assumed rho is sea level standard pressure. Now, the true airspeed, not the indicated, the true airspeed looks just like it, except it's the real rho. So you have to take the indicator, what's on your pressure gauge, I mean your airspeed indicator in the cockpit, you have to multiply that by just the square root of sea level density, which is a constant, sea level standard day, divided by the actual rho. And that gives you the true airspeed of the airplane. And what you often do is you can dial in the atmospheric pressure and temperature of where you're flying to get rho. But the way an airplane flies, okay, if you're taking off out of Orange County on a standard day, here's all you need. Standard day, 59 degrees Fahrenheit. Now, as you go up in altitude, that standard day, the true airspeed's the same. But now you climb up to 10,000 feet, your true airspeed is higher. And 20,000 feet, your true airspeed is still higher. But an airplane, we talked about the aerodynamic coefficients. CL is equal to weight over wing area divided by Q infinity, dynamic pressure. And that's what gives you your lift and your drag. So it'd be nice to fly at constant Q, constant dynamic pressure. Well, that's just constant P0 minus P. Flying at constant P0 minus P, your true airspeed is higher. And most commercial airplanes, even up to 35, 40,000 feet, fly at constant indicated airspeed. That's why you want to fly high, because in fact, you're going a lot faster. I used to hang people up in MAE 158 with that. I tell them, okay, you're going to fly at constant indicated airspeed. And you find out that at constant indicated airspeed, your drag is constant and that you're going a lot faster. That's why you try and fly high. All right, we're learning a little bit here. How far do I want to get into this? A little further, yeah, We're gonna review this. I got you drinking from a fire hose maybe here a little bit. Incompressible inviscid flow. I didn't say irrotational yet. Incompressible inviscid flow. I'll bring irrotationality in pretty soon. Here's the continuity equation, and okay, gee, you got to have it non-steady, but we're going to have steady and incompressible, and this gets pretty nice. And now I say, if it's also irrotational, we have velocity potential, we say that's this. And also, remember I said del of del phi is equal to 0, or we get del squared of phi equals 0, which is Laplace's equation. And it looks, this is an equation that shows up in partial differential equations and gets beaten to death because it has such nice solutions and it's linear. So you've seen that before. You've probably seen it in double E course. Now, okay, we're talking here about the velocity potential. What about the stream function for 2D flow? Incidentally, this works for 3. I've shown it that way. And we have u is partial psi with respect to y, v is minus partial psi with respect to x. And another way to write the continuity equation down is to say it's equal to partial u with x plus partial v with respect to y, v equals 0. Now, if you try and say, well, let's put in these definitions of psi, stream function, you get this, which is trivial. Second partial of psi with respect to x and y is the same as the second partial of psi with respect to y and x, trivial. So this isn't helping us right now, except the second condition for irrotational flow is this. And in terms of psi, then we get, bingo, psi satisfies Laplace's equation. Here is phi doing it, here's psi. So okay, if we're going to use the stream function, it's got to be 2D. It doesn't work in 3D. And just this factor makes a big difference in flow solutions. That's why we call it potential flow instead of stream function flow. But for 2D flow, this gives us some real weaponry to solve flows. One is that any irrotational incompressible flow has a velocity potential, satisfies Laplace's equation. If the flow is two-dimensional, it also has a stream function, satisfies Laplace's equation. Conversely, any solution to Laplace's equation represents phi or psi for a real flow. Now, is it meaningful? Who knows? But any solution to Laplace's equation defines a flow. And I brought up over here, it's linear. So we could have an array of solutions and we can add them up, and that's another solution, as many solutions as we want to add. So what we're going to do next, but I think not today. Well, I wanted to talk about this first. Again, you've had, I think, a partial differential equation course by now. They don't call them partial differential equations. Multivariable calculus, I think, is the term used. I'd never heard that before, but it's because I'm old. A partial differential equation needs more than just that equation to get a solution. It needs boundary conditions. And if you have Laplace's equation and there's a class of solutions, where what do you need to know? Well, let's talk about an airplane. Well, we'll talk about the two-dimensional solutions first. It turns out with Laplace's equation, if you know the conditions at infinity, this is for flow, if you know the conditions at infinity, well, we do. We can say that little u is just v infinity and little v is 0. This is parallel and uniform flow arriving at the body. So this is easy to represent. Well, that's not enough to really get the solution to Laplace's equation. So what do we know at the body? We know its shape. So v dot n or del phi dot n is 0. The flow isn't going into the body. Get it back. And the other thing is psi on the surface. Remember, that's a streamline. The body is a streamline now. is constant. So partial of psi with respect to S is 0, where S is the streamline direction. For 2D flows, we've milked this dry already. dy dx of the body defines V over U at the surface. And noting always that in viscous flows, the velocity is 0 at the wall. That's called zero slip. I don't want to start this. Here we're starting to get answers. I want to go back to emphasize some stuff. We wrote down way back here. I'm trying to give an idea. We've covered a lot of ground. And we said the first thing I won't go back into the vector identities, but we started with the, here we go, continuity equation, not knowing just saying, hey, there's air, and we allowed it to be compressible and everything, and wrote down some general equations. Just saying, hey, if it's air and it's constant density, a general relation, the most general relation we could derive is this one. Came out pretty simple. If we say, hey, it's steady flow, we allowed it to be unsteady. Let me back. I'll come back down. We allowed it to be unsteady, but hey, this is the easiest one. Didn't know anything else about the air. And here we didn't, in continuity, we didn't mess around with viscosity. Incidentally, another key here is we don't have a body in here. So just the flow going along, you don't need viscous terms in here. But then we moved on to the momentum equation, and all the continuity says what goes in has to come out. Well, in momentum, you got forces, and if there is, incidentally, the continuity equation works just fine if you stick a body in there. So then we said, what about momentum? And we included we got romantic and had body forces and put a placeholder in for viscosity. Certainly it's a force. Counts for a lot of the drag on an airplane. So we had to allow for that just as a placeholder. And we looked at unsteady flow, and we came up with, this is just pushing math around and jumping from surface to volume integrals and so on, and then saying, hey, if something vanishes for all, we didn't define, boy, I gotta fix this, sorry. Again, we didn't define, this is arbitrary. Well, if it's arbitrary, then the integrals over the surface and the volume, hey, it just, it's got to work for all of those. So we play around and get everything. Okay, here we had it into getting close to all volume integrals, and but we can, using the divergence theorem, we could get there. And here it is, the momentum equation, and it's a vector equation. So we broke it up into 3 equations just to make it more handy to use. And then we say, since the volume is arbitrary, you get 3 differential equations. And then we said, hey, we're not going to, we're going to have inviscid flow, and it reduced down to these 3 components. The one we will use most is the x direction Euler equation, but there we are. And at this point, we said it was steady and inviscid. And then for completeness, we did the, yeah, I'll stop here with we wanted to do a problem. We had momentum and continuity, and that lets us solve a lot of problems. This is, again, a very nice example of drawing a control volume and getting an answer. An example of failing to account for a control volume was made public by Boeing when, at the time, this is about almost 20 years ago. Boeing, there was rumor that the airlines wanted an airplane bigger than a 747. And the 747 was, and still is, a spectacular airplane. It was way ahead of its time. First wide body. And it was an outgrowth. The Air Force put out an RFP, request for proposal, for a new giant transport. Douglas had an input on one, Lockheed had an input on one, and Boeing had an input. The Lockheed one with the C-5, which is still in existence. It's delicate, it's rarely flown, but they won. Boeing had, in essence, designed the 747. And the reason they put the cockpit above on a second deck was to allow the nose to open up to load cargo. But there they had this airplane pretty thoroughly established. So in a very brave moment, they said, we're going to build a commercial airplane out of this thing. And in about 1970, it made its first flight. And they were okay, we're going to do that, and started building them. And there was a huge non-recurring cost. That's the money. If you're building a commercial airplane, a company has to foot all the non-recurring. That's all the money in research, design, and certification. Once they start selling the airplanes, then they recover all that in principle. But there's a real big dip in the cookie jar while all that development is going, design and development is going on. And the sales of the 747 were slow initially. And I remember I was up in Seattle heading back down here, and there was a huge billboard that by the airport said, will the last person leaving Seattle please turn off the lights? I mean, it was very serious. But within not too long a period, it started selling okay. And then it became the cash cow for Boeing for many years. And down the road, way more recently, Boeing had developed, the best one was the 747-400. If you've flown on a 747 recently, it's been a 400 model. It was an excellent airplane, still is, and it was making money. And then all of a sudden we did the 777 and got rid of two engines, and the operating cost comes down when you do that. But the other thing that was, we did a super, what was it? The 747-500. That was an excellent airplane to compete with Airbus coming out with the A380. And it didn't sell because the A380 has a full length upper deck and the 747 doesn't. So Boeing panicked a little bit. And what are we going to do about, and the numbers for an A380 or a 747 500, I knew the program manager for that very well. They were better than the A380. Cost per seat mile. It's kind of the one fundamental parameter. But it didn't sell because the Dash 500 looked like the 400, whereas the A380 looked different, and it had full upper deck. They had essentially the same passenger capacity. So Boeing panicked, and I was surprised at it. They came out with an airplane in, I'm going to guess, 95 maybe, called the Sonic Cruiser, where instead of carrying a whole bunch of people, it would fly at 0.95 Mach number. And all the subsonic transports were flying at, I think our airplane, a DC-10 or an MD-11 was 0.84 cruise Mach number. 747 is 0.86. It's the highest cruise Mach number of any commercial airplane, but still it didn't catch on. So the Sonic Cruiser was supposed to be to offset the A380 or whatever. It was not wise. It didn't close. And it had, was kind of like, just look at the Concorde. The engines are under the wing, and that's where you want them for that kind of an airplane. Well, the Sonic Cruiser was born out of Boeing had been trying to do a supersonic airplane to compete with the Concorde. And so it had a similar configuration with the engines underneath. And all of a sudden they came out with this thing that and they had tried to optimize it so that, as you know, you can't fly supersonic over land because of the sonic boom. And that's it's not written, do you hear a boom or not? If m's greater than 1, you can't fly. So Boeing had worked real hard on making its subsonic cruise of a supersonic airplane, making it work very well at 9.5 Mach number for flight over land. Well, let's just make that and not go supersonic with it. You can go to different engines and so on. And they came out with it. Kind of what, and I was working there at the time, and I think, why? That doesn't work. Why am I bringing this up? Okay, they said Engineer X. I know who the poor bastard was that was in Engineer X too. If you look at the flow coming into the engines, it's slowed down as it arrives at the inlet to the engine. And so the static pressure goes up, increases. And you say, well, look at then all that wing ahead, the big delta wing ahead of that is getting a higher pressure, free lift. Draw a control volume. And okay, you've got this flat plate with an inlet below it, right? And yes, the upstream pressure as the flow is arriving there is increased. Now it goes into the inlet, but with that increased pressure, there is flow deflected down. And now when it goes in the inlet, it's straightened out. And you do the math and there's no benefit. I mean, it's deflected down by the wing, but it's coming straight out the back of the engine. And hey, that momentum change to take the downward flow into the engine and straighten it out came out exactly equal, what a surprise, to the free lift. A fundamental error in the control volume. Time and again, I see that. And another rule that we engineers lose sight of all the time is the square cube law. Have you heard of that before? It sounds almost silly, something that Jimmy Kimmel would talk about, or the nighttime comics. But anyway, square cube law, but it's very real. It's as fundamental as you can get. And what's it useful for? Consider an elephant and a mosquito. They're quite different. They're very different in size, which is going to be important in a second. They're very different in size, and they're also very different in geometry. But if you scale up the mosquito to be the size of an elephant, its legs will still be tiny compared to the elephant's. Why is that? Because they're little to begin with. Square cube law is, if you scale something up, areas go up by the square of the length scale, volume and hence mass goes up by the cube of the length scale. And that's why an elephant has great, big, thick legs, because it's walking on them. And historically, there's a sad case here in Irvine where they had something called Lion Country Safari. You could drive in and they had all kinds of animals in there, tigers and elephants, zebras, and a hippopotamus. And you may not know this, but a hippopotamus has to be in the water to sleep because it cannot lay down. If it lays down, it cannot get up. Square cube law again. And I can't remember, they had a name of it. Here's something you can't believe. It was a female hippopotamus and it got out of Lion Country Safari, or it was missing one day. And they couldn't find it, literally. How do you not find a hippopotamus? And after a couple of days, they found it in a field dead because it had finally worn out and died. But the square cube law, when you scale something up, can really hurt you. It's the same reason that tires on little cars don't wear out as fast as on big cars. One other quick aside, and then I'll shut up, is the LA Times had a thing on about people like to pick on SUVs and the big trucks, and they're tearing up the roads. They should be taxed for putting so big a load on a road. Well, it turns out a road bicycle is hard, in principle, harder on the roads. One that's got 110 pounds of air in its tires, so you can go fast. The load on the surface is exactly equal to the tire pressure. Just do a free body diagram. And if you got 35 pounds in your tires, that's the load. You're putting 35 pounds per square inch of load on the pavement. Or a truck will have 70 pounds, but a bicycle has 110 pounds of certain kinds of them. So square cube law, and that's simple. And there are people that will not believe that a truck versus a bicycle, which one puts the higher load on the pavement. So again, go through this example carefully. You got another homework problem on lift, where you've got to do a different not free body diagram, define a control volume to measure lift. Here we got drag for you. So, okay, I didn't want to get into the next part yet. And so with that, are there any questions? Okay, well, in that case, we'll see you, I guess it'll be Monday. You made it through 2 weeks and everybody's passing so far. So, all right.